Now, in addition to dynamic power, where we're sending clock and data signals that are toggling through logic, and the transition of charging and discharging capacitors is consuming power, we also have static power. And static power is consumed even when the chip is quiescent. In other words, when the chip is not doing any, it's not actively toggling any internal nodes. So you still have voltage supply and a power supply going to your logic, but it's just holding the values that it previously had are all staying static state. Either everything that was a 1 previously stays a 1, everything that was a 0 stays a 0. In this case, we still do have leakage power that draws power from nominally off, quote-unquote, devices. So the device could be, let's say, an inverter whose output is driving a 1. If its output is driving a 1, it means the PMOS device is turned on, but the NMOS device is turned off. So the PMOS pulls its output capacitance up to a 1, and the NMOS is turned off, but that nominally off NMOS has leakage going through it. So that leakage is going to consume some power. Same would be true if you had an inverter who's pulled down to 0. The NMOS device would be on, but the PMOS device would be off, and the PMOS is leaking in that case. So in either case, whether you're pulling to a 1 or a 0, there's going to be some leakage going through the device that should be turned off. In addition to this, if we have some sort of ratioed logic like the pseudo NMOS, which I don't like because that type of circuit will burn a lot more power than leakage power. You have a device that's turned on and it's always on to some extent. It's not ever turned off. But if the like in pseudo NMOS, the device that's turned on is trying to pull up to 1, but the devices on the pull down stack are able to override and pull down near to 0, and that device that's trying to pull up to a 1 isn't just leaking, it's not turned off, it's actually turned on, it's just not a really strong device. And so that's going to burn a lot of power in terms of, it's not leakage power because it's not turned off, but it's active power that's contention power almost, that is going to be drawing a lot of power. And so in particular, if you have some sort of ratioed circuit or pseudo NMOS or something, when you know that it's not going to be doing anything for a while, you almost have to have some way of turning off that contention because it's a lot of power to consume. Now let's revisit our example that we used for dynamic power example several slides ago, but do it for static power in addition this time. So we had that, remember we had that IC chip with 1 billion transistors on it, and 50 million of them were logic and 950 million were memory. So let's do an estimate here where we're trying to estimate static power consumption, and we have a process that has 2 different VT types of transistors. We have a normal VT, or what we're calling a normal VT, which is our quote-unquote fast device, but it has a leakage of 100 nanoamperes per micron. Then we have a high VT device, so the higher VT will mean that it's a little bit slower than the normal VT, but its leakage is a factor of 10 less. So we're going to use the high VT device on paths that are not our most critical paths, and it will help us save leakage power, even though those paths will get a little bit slower, but since they're not the most critical paths, we don't need them to be the fastest transistors out there. So we're going to use the high VT in all of the memories because we have so many memory gates, and in 95% of the logic gates. So only 5% of our logic gates are in the critical path that need to be the fastest, and the other 95% are able to use the hide VT device. And then of course we have gate leakage. All of the gates, whether they're normal or high VT, have the same leakage of 5 nanoamp per micron. And let's assume that junction leakage is negligible in this particular case. So go through, and you can pause here, and I'll go through the solution if you want to try and go through the solution yourself before I go through it on the next slide. Now let's go through the solution to our static power example. So first we want to look at what is the total nominal or normal VT width of transistors and what is the total width of high VT transistors. We'll begin with the normal VT. We said only the logic transistors would be normal VT and only 5% of them. So we had 50 times 10 to the 6th or 50 million logic transistors. Their average width was 12 lambda, and then of course our process was 0.025 or microns or 25 nanometer per lambda, and then only 5% of them were normal VT. So we multiplied that by 0.05. That gives us 0.75 times 10 to the 6th microns of normal VT transistor width. Next we'll go through the width for the high VT transistors. We have, again, for the normal logic, static logic, or combinational logic I should say, we have 50 times 10 to the 6th logic gates. 12 lambda is the average width of each gate, and then 0.95, 95% of them are high VT. So that gives us the combinational logic total width, and then the next we have to add to that the total width of the memory. So the memory cells, we said there's 950 million, so 950 times 10 to the 6th, 4 lambda, that gets multiplied by 4 lambda as the average width of the memory transistor, and then those two get added together and multiplied by our process parameter of 0.025 micron per lambda, and that gives us a total width of high VT of 109 times 10 to the 6th high VT. So once we have, now that we have the total normal VT width and the total high VT width, we can calculate the the current that's through due to subthreshold leakage. So I sub, we take the normal VT times 100 nanometer per micron width of the leakage for the normal VT, multiply those together, and then add to that the total width of the high VT times 10 nanoampere per micron, and then that value you can see is divided by 2. The reason for the division by 2 is a key reason, is for each gate, on average, if it's high or low, whether it's high or low, only on average half of the transistor width is leaking. Keep in mind, let's say for example if we have an inverter, if the inverter is pulling low, the NMOS device is fully turned on, so the NMOS device isn't leaking. The PMOS device is what's leaking. And then if we have a different inverter that's pulling high, the PMOS device is fully turned on and only the NMOS device is leaking. So on average, if we have a bunch of inverters, only half of the transistor width is actually leaking, the other half of the transistor width is turned on. So we take total transistor width and the total leakage determined there, divide by 2 to get our total leakage, because only half, again, half the transistors are leaking. And that gives us 584 milliamps worth of leakage. For our gate, we just take the total W for nominal and total W for high VT, add them together, multiply by 5 nanoamp per micron, and similarly, same argument that we just went through for the subthreshold leakage, we divide by 2 because only half of the gates are leaking depending on if the input to an inverter is high. The PMOS gate isn't leaking because the gate is tied high and the source is tied to VDD, and so you don't get leakage through that. Whereas the NMOS device has a high voltage between the gate and the body, so the transistor that's turned on has a high voltage across it and has the high leakage. So only on average half of your transistors have gate leakage going through them, and so again you have the divide by 2. For your total static power, you take your currents, the total currents that we just calculated, I subthreshold and I gate, add those currents together, multiply by your voltage. I times V is your total power, and in this case it comes out to your total static power is 859 milliwatts of total static power. I'm going to go through this slide kind of quickly. We've talked about subthreshold leakage previously in a previous lecture, but I just wanted to go through it again here. The equation here for subthreshold leakage is approximately I off times 10 to the power given there in the equation, and where I off is defined as the leakage that you'll get when VGS is 0 and VDS is equal to the full value of VDD. And so this I subthreshold equation is true as long as VDS is greater than about 50 millivolts. So when VDS is too low, then of course your leakage goes down by a lot. But as long as it's greater than about 50 millivolts, you'll get that equation there. And some typical values in, let's say, 65 nanometer process is if your threshold voltage is 0.3 volts, you'll get 100 nanoamperes per micron of gate width. If your threshold voltage is 0.4 volts, you'll get 10 nanoamps, so your leakage goes down by a factor of 10. And 0.5 volts, it goes down by another factor of 10 to 1 nanoamp per micron of gate width. And so in effect, you're getting 100 millivolt change in your threshold will give you 1 decade worth, or a factor of 10 difference in your off current. And so it can have changing your threshold voltage by quote unquote a small amount can have a very large logarithmic type effect on your leakage. So so that's one way, one of the reasons why they use multiple VT devices in a process technology. You might wind up seeing a nominal VT, a high VT, and then even ultra high VT or something like that in order to reduce your leakage as much as possible on non-critical devices. Another leakage effect that's definitely worth mentioning is what we might call the stack effect here. So if we have, let's say, shown here on the right hand side, kind of a NAND type stack for an NMOS, two NMOS devices in series with each other. If we turn both of those transistors off, since we have two devices in series, in effect, we'll have less leakage than you might predict if you were just thinking about it. Normally, you might say, oh, maybe the leakage goes down by a factor of 2 or something because you have two series devices, so it's twice the length or something. But in effect, it goes down by quite a bit. And the reason for that is, so the first device will leak a little bit and cause the VX node in between N2 and N1 to, because of the leakage going through N2, it will actually increase the voltage at Vx. And as that voltage increases and goes larger than 0, keep in mind the gate voltage of the transistor N2 is at 0. So its VGS is now going negative instead of being 0. And that effect, I'm not going to go through the full equations down there, but in effect, because VGS is going negative, you get a dramatic decrease in the amount of current through that N2 device, more so than the amount of leakage through the N1 device. So in effect, as a rule of thumb, if you have a stack of 2, you can get your leakage reducing by about a factor of 10. And if you do a stack of 3, it can reduce even further. I'm not going to go through the derivations for a stack of 3 or 4. It's probably better to try and simulate it and get a more precise number through, simulator on a given process technology, because every process technology is going to be a little bit different in the leakage versus, and based on your VT and a lot of other effects. But definitely having a stack of 2 can reduce your leakage by a fairly dramatic amount as long as both devices are turned off. So we can use some of the factors that we just talked about to try and control our leakage and reduce it depending on our use cases. So as I mentioned in some earlier slides, we can use a trade-off of leakage for delay by using the VT, high VT and low VT devices. So we can use if we have multiple VT transistors, we can use the low VT transistors only in our most critical circuits where we need the fastest delay. And typically that's less than 10% of your transistors will need a low VT, maybe down to 5% or even lower, depending on the integrated circuit that you're designing. And 90, 95, maybe 98% of your transistors are a higher VT. And if you have a process that maybe has 3 VTs, you might have something like 80% on really high, ultra high VT, and 10 or 15% on a high VT, and then 5% or less on a low VT or nominal VT. And again, you can use the stack effect to potentially have some circuits where you maybe have an extra transistor in series with them. Sometimes this is called a power gate, where you might have a really large transistor or a lot of parallel transistors that transistor is in series in effect with your power supply going to your logic. And when you know you're not using that logic, you can kind of turn that transistor off and have that off in series with all of your normal logic, and wind up getting a really large decrease in your static leakage. And then finally, you can use reverse body bias, so you can change your body voltage or bulk voltage, depending on what you want to call it. And keep in mind, if you reverse bias your body, your VGS and VGB, or your bulk to source voltage, can modify your threshold voltage. So doing a reverse body bias voltage increases your threshold voltage, which decreases your leakage. So you can do something like that in order to decrease your leakage by increasing your threshold voltage due to reverse body bias. Or you could try to forward bias your body when you're in active mode in order to reduce your threshold. In either case, trying to monkey around with your body bias voltage is a lot more difficult than some of these other effects, and so it's probably done less often. But if you have the right circuitry and the right expertise to do it, it is a mechanism to try and reduce your leakage. As far as gate leakage goes, keep in mind that gate leakage is an extremely strong function of your oxide thickness and your gate to source voltage. So now I mentioned this many times in previous presentations, previous weeks, that the gate leakage was pretty negligible for older processes, and it's become more stronger in more modern processes. This has gotten better when they went to actual metal gate with a high gate or a high K gate. So more exotic gate dielectrics instead of using silicon dioxide. One of the comments that I will make is that for a while the PMOS actually had an order of magnitude less leakage than NMOS. I'm not going to go into the physical reasons for that. And as the oxide thicknesses got even smaller and smaller, eventually we had to go to high K gate dielectrics in order to try and remove a lot of the leakage that was going through the oxide, and that actually has helped the gate leakage a lot. But even with this, some processes will actually provide multiple oxide thicknesses, and so in order to reduce gate leakage. And in particular, if you have I/O transistors or transistors that need a larger voltage in order to run the transistors, you definitely need a thicker oxide in order to withstand the higher voltages without causing tunneling through the gate and without causing extreme amounts of leakage through the gates. And of course, as with any of the leakage parameters, in this particular case for the gates, limiting the voltage that VDD is allowed to be will definitely limit your leakage through your gates as well. So on this foil, it goes through an example for a NAND 3 and talking about leakage, comparing subthreshold leakage and gate leakage in order to get total leakage, depending on the value of your inputs. There's a lot of information in this foil. I'm not going to go through and talk through all of it. The main thing to note is, of course, if you have more of your inputs are 1, and depending on the combination, you can see a dramatic difference in the amount of leakage. So if all 3 of your inputs are 0, your total leakage will be 0.4. I think that's in the nanoampere range. It doesn't say for certain in the slide here. But if all of your inputs are 1, you're going to be leaking through all 3 PMOS devices and also have a lot of gate leakage through the NMOS devices. And so your total leakage goes up by about a factor of 100. From 0.4 up to 46 or almost 47 nanoamperes. So there is, if you want to go through the details of this, it's in the book, chapter 5, I believe 5.3, section 5.3. So I'd suggest going through and reading it in detail. It would take way too long to go through all of this in the lecture. So just keep in mind, like I said, there can be almost a factor of 100 difference in your leakage depending on what your inputs are in this particular case. So the stack effect really can help you, but if your logical input values are not turning off the stack, then it doesn't help you at all, and you get the maximum leakage. And finally, the best way to reduce your leakage is to use what's called power gating. And I kind of mentioned this in a previous foil 1 or 2 slides ago. And in effect, you can use a series of parallel, or not series, a parallel set of transistors that are in series with your voltage supply, so your VDD supply, in order to, and you make these a lot of parallel transistors. So you basically want to provide your voltage supply through with virtually no voltage drop across your transistors. So you need a lot of them in parallel in order to send the output of this parallel bank of transistors to a block of logic. And if you turn all of those, let's say in the circuit that's shown on the right there, those transistors, if you have a sleep value that's controlling it, when you're not in sleep, sleep is 0, and so it turns those transistors fully on. You allow VDD to go through those PMOS transistors and power up that power gated block. And so when you're using that block, you have all of those transistors on, and you provide something that's really close to VDD to that entire block of logic. Now, when you know that that logic isn't being used, you can have sleep go to a value of 1. It turns off the current through all of those transistors, and that entire block will now act like it's got a stack of PMOS that's turned off in series with it, and so its overall leakage will go down by a factor of 10 or potentially more, depending on what the internal logic is. If you have other logic in there that has multiple series PMOS, you could see it drop even more than that. But in effect, you can get a very large drop to your leakage by completely turning off the power to a given chunk of logic that isn't being used at a particular point in time. So one thing to keep in mind is there will be a slight voltage drop across your sleep transistors, and so that slight voltage drop will degrade the performance of that power gated block in normal operation. But as long as you make the number of parallel sleep transistors large enough for the amount of current that needs to be provided to the block, you can minimize that impact and see a fairly small impact to your overall power while you're trying to do real logic, at a pretty dramatic decrease in your leakage power when you're trying to turn it off. And then, of course, if you need to turn your sleep transistors on or off, because you have so many of these sleep transistors in parallel, that's a lot of capacitance. So keep in mind, you don't want to turn it on and turn it off on a cycle by cycle basis. In effect, you wouldn't be able to do it one cycle to the next anyway, because it would take a while for your voltage to stabilize on the other side of the sleep transistors. But you wouldn't probably even want to do it on a 20 cycle basis or a 50 cycle. You'd probably only want to do it when you know that you're going to be sleeping for long enough, maybe 100, maybe a couple hundred cycles. If you know you're going to be sleeping long enough, you can turn the logic off for a longer period of time.